So we went through the test in class, but let's go ahead and take a quick look at it again. A measure of an atom's ability to attract electrons to itself, that is electronegativity. Remember, that increases from left to right, and it increases for the group A elements anyway, and it increases up the group. B, an especially stable valence shell electron configuration. Sometimes we call that a complete octet, and that's when you have, it's called NS2, NP6. It's also called the rare gas configuration, or rare gas or inert gas or noble gas configuration. For C, I was after ionic bond is when electrons are completely transferred to create the metals generally create cations, transfer electrons from metals to nonmetals. Nonmetals create are anions, negatively charged. Speaking of, D, the general name for a negative ion, that's called an anion. E, molecular weight is the term that describes the mass of a single molecule. And of course, if you're talking about ionic compounds, it would be not molecular weight, it'd be formula weight. For F, I was after molar mass is the term that describes the mass of 1 mole of anything, including 1 mole of molecules. For G, the secondary covalent bond where electrons are shared, that's the pi bond. And for H, a bond where an electron pair is being shared in general is called a covalent bond. So down here for this part, you were supposed to say whether this represents an ionic compound or a molecular compound. And I really emphasize in lecture that you look for the metal. And if there is a metal, then that means that that metal has given up electrons to form a cation, and it's an ionic compound. So the asterisks here are metals. So sodium's a metal, so it's an ionic compound. Sulfur and oxygen are both nonmetals, so it's a molecular compound. We consider hydrogen for this purpose nonmetal, so carbon and hydrogen nonmetals, molecular compound. For D, I took either, but actually nitrogen and hydrogen would be nonmetals, and bromine's also a nonmetal, but as we found in this course, NH4 actually is ammonium, so this is an ionic compound, but I would take either. E, phosphorus and chlorine are both nonmetals, so molecular compound, and for F, magnesium's a metal, so that makes it an ionic compound. For this section, I gave you the component ions, and you needed to write the neutral formula. So it's the crisscross. So that's to say, since I have 2, the magnitude of the charge on the anion is 2, I'm going to need 2 cations, sodiums, and the magnitude of the charge on the sodium is 1, so I'm only going to need 1 SO4. For the next one, for B, if we crisscross, and sometimes this gets a little bit confusing, but we need 3 of these. The magnitude of the charge on the cation is 3, so that means we need 3 anions, and it's a polyatomic anion, so we have to put the hydroxide group, the OH group, in parentheses and put the 3 outside. Excuse me. C, when we crisscross, we need 2 of those chlorite groups and only 1 calcium. For D, if we crisscross, we will need 2 of the fluoride ions, and of course Hg2 will need 1 of those. For E, we crisscross, we need 2 of the Fe's and 3 of the S's. So the next 2 sections are also about ionic compounds and what call either making the neutral formula unit or naming them. So in this case, I gave you the name, and like I said, I really suggest that you write the cation and then the anion. So in this case, lithium is the cation. You can find it on the periodic table, so it's a +1. And then you needed to memorize the hydrogen sulfate. So sulfate is SO4 -2, so hydrogen sulfate is HSO4 -1. So of course we crisscross and we need 1 of each. So again, I really emphasize write the component ions. So copper 1 would look like this. Okay, and oxide, of course, it's a 6A element. It picks up 2 electrons, so it would be a -2. If we crisscross, we get Cu2O. Potassium carbonate. Potassium you can find on the periodic table. It's a +1. Carbonate is one of the things you had to memorize. It's a CO3 2-. Then if we crisscross, you can see it's K2CO3. Calcium perchlorate. So remember the halogens, several of them form these oxyanions, and the 8 means lots of oxygen, and the per means even more oxygens than lots. So that's our ClO4 minus 1, and when we crisscross, we need 2 of those, so I'm going to put that in parentheses, and only need 1 calcium. Sodium nitride, remember if you see the IDE, that's a monoatomic anion. So we find nitrogen on the periodic table. It's a 5A. It picks up 3 electrons to be a -3. So then when we crisscross, then we have 3 sodiums and 1 nitrogen, because of course sodium is a 1A, so it loses that 1 valence electron to be a +1 cation. Silver iodide. Silver was one of the 3 special transition elements you need to memorize. It's always a +1. And iodide, again, we're talking about the monoatomic anion, IDE. So it's a -1, I minus 1. So a crisscross will need 1 of each. Tin 2 bromate, you needed to, actually in the previous unit, I think it was the previous unit of material we talked about, you need to memorize some of the symbols. So the symbol for tin is SN. The Roman numeral 2 means it's a +2. Then bromate here, it's a bromine sort of containing oxyanion. The 8 means it has a fair bit of oxygen, so that's the BrO3 minus 1. Crisscross, and of course you need 2 of those bromates and only 1 of the tins. Iron 3 sulfide, again IDE, you're looking at a monoatomic anion, and since it's 5A, it picks up 3 electrons to be a -3 anion. So this is a case where actually you have a +3 for your cation, a -3 for your anion. They actually, if you get 1 of each, it's neutral. Okay, so if you crisscrossed, I think I still gave it to you, I think. If you had Fe3P3, I still gave it to you. So good job, nothing bad there. Ammonium, of course, is NH4 plus 1 cation. Nitrate is the NO3. Oh, I missed my minus. NO3 minus 1 here. If we crisscross, we only need 1 of each. And then down to here where I give you the formula and you have to give me the name. Again, it's always cation anion, so look for the cation. So of course K is the cation, SO3 is the anion. Specifically K is a +1, SO3 is a -2. The name of this is potassium sulfite. Remember that sulfate is SO4 2-, sulfite is SO3 2-. What was I going to say? Oh, I think what I was going to say is for this one, you know, it really didn't help necessarily to make the component ions. I just think it's a good habit to get into. Now the next one, I think you had to make the component anions. So here, okay, we have CO is cobalt, S is sulfide. So I went ahead and put a -2 for the sulfide because I knew that, okay, because of the where it's at in the periodic table. 6A picks up 2 electrons, become a -2 anion. So if I actually it's called reverse crisscross, I can actually take the number of sulfides I have and make it the charge of the cation. And of course, this works out just fine because the number of number of cations I need make it the charge of the anion. So anyway, you had to deduce that we were dealing with cobalt +3 because cobalt is one of those where you don't know what the charge is, so you have to say the charge in the name. For the next one, again, it's always cation anion. So Al is aluminum and N is nitride. We don't use Roman numerals for aluminum. Here for D, again, we had to do a little bit of deduction. I think on your exam, if you put the Roman numerals but didn't put the correct Roman numerals, I didn't count it wrong. But if we do a reverse crisscross, our lead is actually going to be a +2 charge, and of course our chloride anion 7A picks up 1 electron, being a -1 charge. So we do need to use Roman numerals with the name of lead. So the charge is what the Roman numerals are, lead 2 chloride. For the next one, we have our metal is calcium, and our cation is a polyatomic cation. It's the bromine one with the least amount of oxygen. So it's going to have an ite suffix, and it's going to have a hypo prefix. So hypobromite is the name of that polyatomic ion. Cool. So down here we have the lithium is the metal, and so Cn-1 is the polyatomic anion. So that's the name of that polyatomic anion is cyanide, and of course lithium, we just don't use any Roman numerals. The next one we do use Roman numerals for, though. So we've got, if we reverse crisscross, we've got a nickel cation with a +2 charge, and of course nitrate with a -1 charge. We do have to use Roman numerals with nickel, so it's going to be nickel 2, the last name is nitrate. For H, we have to crisscross 2. We have chlorine with a -1 charge. That means that if we have one of each, one copper and one chlorine, that means the copper must have a +1 charge. And with copper, we need to use Roman numerals, so the first name is going to be copper 1 chloride. Down here, we have zinc as your metal. And zinc is one of those transition elements that we don't use, the 3 transition elements we don't use Roman numerals for. It has a +2 charge. But again, writing the component ions to write the name doesn't really help or make a difference here. So the first name is simply going to be zinc. Now that HCO3 -1, that's your bicarbonate or hydrogen carbonate. It's the same thing. Okay, now we're kind of leading into Lewis structures. So for this one, for this section, I was after that pot of valence electrons, kind of like we do to draw the Lewis structures. So in the formula, there are 2 nitrogens. Nitrogen is a 5A element, so 2 times 5 is 10, so 10 electrons coming from nitrogen. There are 4 hydrogen atoms according to the formula, and hydrogens always bring 1 valence electron, so collectively they have 4, so 10 plus 4 is 14 electrons. Carbon is a 4A element, 3 times 4 for carbon, plus there are 8 hydrogens, and they each bring 1 electron, so we have 20 electrons for B. For C, we have a polyatomic anion. The fact that it's -2 charge means that I have to kick in 2 electrons for the charge. So carbon in the formula, there's only 1 carbon, and it's a 4A element, 1 times 4 for carbon. There are 3 oxygens. They are 6A element, so 3 times 6 for oxygen. And so the total pot of valence electrons here I have is 24 electrons. Down here, H3O +1. Now the fact that it's a +1 charge means that it's deficient 1 electron, so I'm going to subtract 1 electron from my pot. There are 3 hydrogens, so I'm going to take 3 times the number of valence electrons hydrogen has, which is 1. There's 1 oxygen, so I'm going to take 1 times the number of valence electrons for oxygen, which is 6. So total then I have 8 electrons. And then here to draw the Lewis structures, actually that was my first step in drawing the Lewis structure. For this first one, I have collectively 6 electrons coming from sulfur, 2 times 7 or 14 electrons coming from fluorine for a total of 20 electrons. Now I actually didn't go through all those steps like we did in lab on paper, but I might have in my mind a little bit. Since it's a neutral compound, you expect sulfur to reach out 8 minus its group number, 8 minus 6. So I went ahead and put it reaching out one time to each of the fluorines. Then if you start to go ahead and make the fluorines, each of the terminal atoms have a complete octet, you've used up 6 more of your electrons. And then if you look at what you have left over, you actually have 4 more electrons, or 2 pairs to be lone pair electrons on the sulfur. So that is actually the favored electron configuration, or that's the favored, Lewis structure for SF2. So for the nitrite polyatomic anion, notice that the nitrogen has 1 times 5 valence electrons. There are 2 oxygens. They each bring 6 valence electrons. And I kick in 1 electron for the charge of -1 for a total of 18 electrons. So the least electronegative is nitrogen. We're going to put it in the middle, and we're going to make, remember we learned to make a sigma bond reaching out to the oxygens. When the dust finally settles, to give the terminal atoms a complete octet, and then also the central atom a complete octet, notice I'm going to have 1 double bond. So this is one resonance structure of nitrite. And notice that with 1 point, you had to, each were 3 points, you had to go ahead and put this one in brackets and put a negative sign outside. For HCN, I'm going to put carbon in the middle because it's the lowest electronegative. And my pot of valence electrons look like this, where the hydrogens is 1 times 1, the carbon is 1 times 4, the nitrogen is 1 times 5. So I have a pot of electrons, it's 10 electrons to be drawn on my Lewis structure. Again, if I go back to the number of to the expected valence of the atom, the expected valence of carbon is 4 because it's 4A, so 8 minus 4 is 4. And the expected valence, of course, of hydrogen, it wants to reach out once. Expected valence of nitrogen happens to be 3 because it's a 5A, so 8 minus 5 is 3. And so actually we end up with a triple bond between the nitrogen and the carbon. And then if you count electrons, you still have 2 lone pair electrons we can put on the nitrogen. Br2CO, so we need to come up with a pot of valence electrons. For bromine, it's 2 times 7. For carbon, it's 1 times 4. For oxygen, it's 1 times 6. So collectively, you're looking at 24 electrons. So again, since this is a neutral molecule, we should be kind of looking for bromine. The halogens 7A reach out 1 time, carbon reaches out 4 times. Oxygen is a 6A, so 8 minus 6 is 2, so it should reach out twice. So the favored structure looks like this, with the lowest electronegative atom, carbon, in the middle, and looking like this, a double bond between the carbon and the oxygen. And then we had sulfite down here. So pot of valence electrons look like this. The sulfur is 1 times 6. The oxygen is 3 times 6. And since it's negatively charged with a -2, you need to kick in 2 electrons. So collectively, you're looking at a pot of electrons to put around your Lewis structure is 26. So if we put sulfur in the middle, go ahead and make those sigma bonds to each of the oxygens. Go ahead and give the oxygens a complete octet by putting 3 sets of lone pair electrons around them. If you count up electrons, actually we have 2 more electrons. And so now we can go ahead and put those last 2 electrons, the way I think of it, around the sulfur atom. Now remember, since this is a charged, it's a charged polyatomic ion, the expected rules of valence it doesn't abide by that. So because sulfur, we said earlier, should be what? Both sulfur and oxygen would be expected to reach out twice, and they're not doing that here in this Lewis structure because it's a charged, it's not a neutral molecule. Okay, and then so for here, you were supposed to do a few things. Let's see if I can, oh, good. For the first one, go ahead and say, for instance, this atom A here, this carbon, what is its structural geometry and what is its bond angle? So for each of these, then, to answer that, what I talked about was you count sigma bonds, 1, 2, 3, lone pair electrons, which is none. So 3 plus 0 is 3, so you're looking at sp2 orbital hybridization, which corresponds to trigonal planar shape. The bond angle is 120. So around this carbon atom, we count sigma bonds. I got 4 sigma bonds, no lone pair electrons, so 4 plus 0 is 4. So you're looking at sp3 hybridization, tetrahedral, and 109.5 is the angle. Here for this oxygen, let's see, we got 2 sigma bonds, we got 2 lone pair electrons, so 2 plus 2 is 4. So again, you're looking at sp3 orbital hybridization, tetrahedral, 109.5. For this carbon atom, it's got only 2 sigma bonds, because remember, in a triple bond, it's sigma pi pi. So 2 sigma bonds, no lone pair electrons, so 2 plus 0 is 2, so you're looking at sp orbital hybridized. It's linear, and its bond angle's a hot dog, 180. If you were to count sigma bonds, there are 3. So here's a sigma, pi bonds. If you count pi bonds, there are 3. There's 1 pi bond here and 2 pi bonds here. The next question was let's count lone pair electrons. I get 1, 2, 3, 4, 5, 6, 7. 7 lone pair electrons. For this next 3, each with 3 points apiece, you need to calculate the molar mass. So units of molar mass for compounds and for elements, for basketballs, for anything, it's grams per mole. So the units needed to be grams per mole. So for A, it said you had 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygens. So actually, you can use a periodic table and go ahead and add that up. And round to 2 decimals, I get 84.01 grams per mole. For C3H7F, we have 3 carbons, 7 hydrogens, and 1 fluorine. And get the decimal number from the periodic table. That gives us a total molar mass of 62.09 grams per mole. For calcium bromide, we had 1 calcium, 2 bromines, for some comes to 199.88 grams per mole. Now the instructions were a little bit kind of confusing, so I apologize for this. It says I wanted a minimum of 4 significant figures. And the rule of thumb, and I kind of try to say this in the lecture, the rule of thumb is that if you have something that's greater than 10, you're going to have 2 decimals associated with the molar mass. And actually here, when we are doing this multiplying here, there's no uncertainty brought by the 1 because it comes from the formula. There is uncertainty in the decimal number for calcium. Similarly with the bromine, there's no uncertainty in the 2, but there is uncertainty in the 79.90. So I don't know if you buy this, but you end up kind of then, when you add these, let's see, how do I say this? You get to keep 2 decimals here, keep 2 decimals here, and then you're adding them, so you get to keep 2 decimals. So I don't think I took it off if you went ahead and gave me only 4 sig figs here, but you are really allowed 2 decimals in that molar mass of CaBr2. So the next one, you were to come up with the percent elemental composition. Basically the weight percent brought by carbon, the weight percent brought by hydrogen, and the weight percent brought by chlorine. And in general, good job for making sure you show me all your work. If we go ahead and knock out the molar mass of C2H4Cl2, it looks like this. So the molar mass for the whole compound is 98.95 grams per mole. If we consider 1 mole of the compound, then with regard to carbon, we have 2 times the decimal number for carbon, 12.01 grams, divided by the total mass, and then to get it parts per 100 multiplied by 100%. We're allowed 4 significant figures, so we get 24.27%. Do a similar thing for hydrogen. There were 4 hydrogens in the compound, so we take 4 times the decimal number of a hydrogen, divide by the mass of the whole thing times 100%, we get 4.075%. Again, 4 sig figs, right? So for chlorine, we take 2 times, there were 2 chlorines in it, so we take 2 times the decimal number of chlorine, which is 35.45, and we divide it by the total mass of the molecule and multiply by 100%. That gives us 71.65%. So what I came up with here is 99.995%, which I guess I should have just given it only 2 decimals, and that makes it 100.00%, doesn't it? Okay, so for this one, it was after the empirical formula for these compounds. So if you can, go ahead and take those subscripts and divide by a whole number and get another set of whole numbers, then go ahead and do it. And then that will be its reduced, what we call empirical formula. So in this case, we can take 6 and 12 and 6 divided by 6, and we get 1, 2, and 1. So C1H2O1 is the reduced empirical formula. For B, actually, if this is the molecular formula, then the molecular formula and the empirical formula are the same, because you can't take 5, 10, and 1 and divide by a whole number and get another set of whole numbers. So like I said, the molecular formula and the empirical formula are the same. For this one, the H2Cl2, we can actually go ahead and divide by 2, and that gives us HgCl. So getting down to the last couple of questions. For this question, how many moles of H2CO molecules are there in this mass of the compound? So this is a grams to moles problem. So to go from grams to moles, we know we can use the molar mass of the compound. So kind of up front here is the calculation of the molar mass of H2CO. I need to take 2 times the decimal number of hydrogen plus 1 times the decimal number of carbon plus 1 times the decimal number of oxygen. So that actually, that molar mass, this 30.03 grams per mole, is going to be my conversion factor. If I make the first term the mass that I want to convert to moles, so 1.98 grams over 1, notice I can use the flipped version of the molar mass, 1 mole over 30.03 grams, so grams cancel, we left with units of moles to get to moles. So we've got what, 3 sig figs, so rounded 3 sig figs, I get 0.0659 moles of the compound. Down here, if you have this number of moles of the compound, how many grams is this? So again, to go from moles to grams, we can use the molar mass of the compound, and I knocked it out right here using the periodic table to get to the molar mass of the compound. Then if I go ahead and make my first term the moles that I want to convert to grams, that 0.342 moles over 1, then I'm going to use the non-flipped version of the molar mass, 199.88 grams over 1 mole, to go ahead and have moles cancel, be left with units of grams. Round to 3 sig figs, I get 68.4 grams of compound. So now the last problem of the question. How many moles of sodium ions, Na plus ions, are there in 45 grams of Na2O? Now, the way I work this, you'll see, is I went and took the mass of the compound to get to the moles of the compound. And then the last little bit, I recognized that there are 2 sodiums for every 1 Na2O. So that was the last term you're going to see. So here we go. So I needed to knock out the molar mass of the compound. So 2 times the decimal number of sodium plus 1 times the decimal number of oxygen, 61.98 grams per mole of the compound. Now to work this problem, we're kind of bumping up against this in Unit 4. I was careful to be, what I say, explicit. So instead of just putting 45 grams, I put 45 grams Na2O, and you'll see why. So then the next term is the molar mass. If I want grams to cancel, I have to put grams in the bottom. So 1 mole of Na2O over 61.98 grams Na2O. That will give me moles of Na2O. And then, like I said a minute ago, then I can put 2 moles of Na plus over 1 mole of Na2O. Okay, so then my moles of Na2O cancel. I left with moles of Na. So round to 2 sig figs, then that leaves me with 1.5 moles of Na. So there you have it. Let me know if you have any questions.